Hey there, welcome back to Linear Algebra, section 1.5. We're wrapping up week 2 here. We're going to talk about the very important topics of linear dependence and independence. So as usual, I'll talk fast through these videos. You got to pause them. Hopefully you've already read the section, reread it with me as we're going through it. Some of my examples are their examples. It's a super important material. You got to digest this as we're covering it here. You can see the objectives. I want to motivate a little bit and define what I mean by linearly dependent sets, or just LD sets for short. They're kind of opposite linearly independent sets. I want to characterize those, give a condition to check for it, super important condition. Hopefully show lots of examples, and then I want to prove what I kind of think of as an expansion theorem. It's theorem, I didn't write it down here, it's the theorem 1.7 is the theorem we're going to take a look at out of your text, and we'll look at a statement and discuss the proof at the end. Okay, so let's get going here. As a motivation, it's kind of an abstract motivation, but still, suppose I have some finite subset of a vector space, calling it S. Yeah, you can see it at the top of the screen there. It's got some n vectors in it, chosen from V. And suppose that it's possible, so for some one of them, the ith one, I don't know which number I is, but some number between 1 and n, that the ith vector v sub I is a linear combination of the other ones. All right, so this is my notation for the other ones, right? It's v1, v2, and so on up to I minus 1, right before I. Skip over I, it's not there because I'm talking about everything else. So the next number is I plus 1, and then so on. All right, so suppose that that thing, vi, is a linear combination of these other ones. So here's my question. I've got the set S. It's got the vectors v1 through vn. This is the set for S except for that ith one. All right, this is just set complement notation. So it's S, take away the singleton subset containing vi. How do those spans compare? Stop the video and think about it for a little bit. They're both sets. They're subsets of V, and I'm asking, is there any relationship between them? So I won't pause myself here to make this video any longer than it has to be, but I hope you paused and thought about it. But certainly in any situation, it doesn't really matter about these hypotheses. It's certainly going to be true that the span of S, except for VI, is going to be a subset of the span of S, right? Because I mean, what does span mean? It's linear combinations. If you're a linear combination of elements in S, except for the ith one, well, then in particular, you're a linear combination of elements in S. You're not penalized for not having the ith one in there. So this is sort of just always true. So this hypothesis must have something to do with the opposite inclusion, yeah? And so I claim they're equal. I claim that they are equal. And how to see that, right? What if you take some vector x in the span of S? We just have to remember what the definition of that means. It means that you can write x as some linear combination. I'm going to keep this brief here, but of those vectors, right? S is the vectors v1 to vn. So if you're in the span, you're some combination of them. But if vi, the ith basis vector, let me just sort of carve it out of there, right? I can write this thing as the sum, as the j's that aren't equal to I of aj, vj, plus that ith one. Yeah, plus that ith one. But we're saying that we're talking about the case where vi is a linear combination of these other guys, right? So I'm just going to kind of do it by highlighting. This term can be written as a combination of these other v's, right? So then once you gathered your coefficient, that's exactly what this is. This is a linear combination of those other v's. So once you did that, I'm not going to write out the details, but once you substituted vi as a linear combination of these other v's, you could gather the coefficients and you would have written x as a linear combination, and you wouldn't be using vi anymore. All right, so that's kind of at least a sketch of a proof of why the other one, it goes the same, is also true. The span of S is a subset of the span of S, take away VI. Okay. Okay, well, that's just kind of to motivate. So why do I care about that? I mean, so it kind of leads me to the idea that, you know, maybe there's some minimal spanning subset of S, right? Because if I'm looking at the set S and I have some element in it that is a linear combination of other elements, I can chuck it and not change the span. And what's left is smaller, right? And then I could ask, well, hey, is there anything in here that's a linear combination? Maybe I'm looking for the smallest possible set that spans. You saw spanning problems lead to systems of equations, right? So the smaller the system of the equations, the better I am. So I'd like to have some idea of this. I'm not making a rigorous definition of this, but just some kind of notion, intuitive notion of minimal spanning set. Okay, so here's the result I want to prove. I'm not going to rewrite all the notation using the notation above. S is that finite set of V1 to Vn. But yeah, there is some vector Vi in there that's a linear combination of the others. If and only if you can write all of the vectors in S as a linear combination, but a very special one, a linear combination that equals 0, but not all of these coefficients AI are equal to 0. Okay, so sometimes people call this thing a non-trivial linear combination of the VI. And what makes it non-trivial? It's non-trivial because of this: not all these coefficients are equal to 0. At least one of them isn't 0. So this lemma says that such a combination would exist. Some non-trivial linear combination of the V's equals 0. If and only if you can write VI as a linear combination of the other V's for some I. All right, so let's try to see if we can prove it. I'm going to write the proof out here, so this is going to slow the video down a little bit, but maybe it'll make it a little bit easier to follow. So as usual, I'm kind of using this notation. This direction means I'm going to assume the hypothesis that I wrote first. So I'm going to suppose there is such an I, and I'm not going to write this out in long sentences to keep the video shorter. So I am going to suppose that I've got some I. So there exists some I between 1 and n, and this VI is a linear combination of the others. Okay, so j goes from 1 to n, but it doesn't equal I, and I've got these AJs. They're all elements of F. Okay, so that's my supposition. And then I'm just going to rearrange this equation a little bit. I can rearrange this equation by writing, well, this thing means that I've got the sum as j goes from 1 to n, no condition of AJ, VJ equaling 0, where I'll just define AI to be minus 1. Right? So what am I doing? I'm taking this term, 1 times VI, and subtracting it to the other side. And if I make this definition, then when the counter gets to this old value that it wasn't allowed to equal, now it has a value. It's minus 1. In fact, it's minus 1 times VI. That's exactly the term that would be there. And that expression is equal to 0 because this VI was the only term on the left-hand side of the equation. All right, so that's half the proof. Wasn't so bad. How about proving the other way? I think it's going to go just as smoothly. If we have some non-trivial linear combination, I'm going to write it in summation notation, but I've got some combination of all the V's. Let me not be lazy and indicate that. I've got all of them, and not all the A's are 0. Okay, maybe that's a sloppy way of saying that means there exists some I where AI isn't 0. Okay, so in the same way that we just did, we could take that term, kind of pull it off, AI, VI, and that would equal what? It would equal, well, they would all have minus signs on them. J would go from 1 to n, but it wouldn't be I. It's just the rest. It's a notationally, it's kind of inconvenient, but I'm writing it out, a notationally accurate way of what's going on. Does it make sense? I'm just taking the ith term, subtracting the rest of them to the other side. So that's where this minus sign comes from. And then if I divide both sides by AI, remember AI is not 0. So I'm in a field, just think of it as real numbers. If abstract fields aren't comfortable to you, then what do I have? I have that VI is equal to, if you really want me to make it look formal, I'll push all this stuff through. It's minus AI inverse times AJ, that's my coefficient of VJ, where J is a number between 1 and n, but it's not allowed to be equal to the number I. Okay. Cool. So what does that show? That shows that VI is in the span of the V's, of the other V's, right? That shows that VI is in the span of the other V's. Let's go back and remember what we're trying to prove. We were trying to prove that if that was true, it must be the case that there exists some I that's a linear combination of the other V's. Well, that's exactly what we've done, right? It's this one. This is a linear combination of the other V's, so our proof is complete. Cool, right? So that's all kind of a motivation, if you like, for this definition. Very important definition. One of the absolute key concepts of the whole linear algebra course is this concept of linear dependence. All right, so based on that lemma, I'm going to rephrase the lemma below in a second, but we're going to call a non-empty, it has to be non-empty by definition, a non-empty subset is called linearly dependent if you can find vectors in it, some finite number of them. It can be 1, it can be 100, it has to be at least one of them, and then some scalars that aren't all 0. That's the crucial part. I'm going to highlight it too. So these scalars in the field, all but one of them can be 0, but not all of them, not all 0, such that the linear combination of those vectors is equal to 0. If you can find such vectors, then it's called linearly dependent. All right, so the lemma just says, if we rephrase the thing, the lemma just says that our set's linearly independent if and only if some vector in the set S is a linear combination of the other vectors in the set S. All right, so you can think of, I could have made that the definition, but I'm going for this one. Okay. Equally important is the kind of antonym case. We're going to call a subset linearly independent if it's not linearly dependent. All right, so given a subset of a vector space, it's either linearly dependent or it's not. And in the case that it's not, we're going to call it linearly independent. These are just some sort of nitty-gritty things, but it's a nice place to say them. The empty set is linearly independent because it's not linearly dependent, because linearly dependent sets were required to be non-empty, right? So technically speaking, the empty set is a linearly independent set. It'll fit later on. I can kind of come back and see why that's a nice idea to do that. If the 0 vector is in a set S, I'm just kind of going over some facts here. If the 0 vector is in a set S, then it would always be linearly dependent. Does that make sense? Because if 0 was in your set S, yeah, isn't it possible to choose a subset vectors and a combination like this? You could just go, well, go like this. If 0 is in your set S, take the scalar 1, take any scalar you want, multiply it by 0. Yeah, that's a linear combination of elements in S, and it equals 0, but the coefficients aren't 0. So 0, if 0 is in your set, then your set's always linearly dependent. So if we have a linearly independent set, we never have 0 in it, is another way to say that. The singleton set containing 0 is linearly dependent. Conversely, though, I'm kind of down here now. If you take a non-zero vector, then the vector that contains exactly that vector is always linearly independent, right? And how to check that? Well, let's just see. If it were dependent, if this set were linearly dependent, then there must be some linear combination of vectors in it. There's only one vector in it. So there must be some A, I'll just call it, times V that's equal to 0. Yeah, but if V isn't 0, then A has to be. Right? Because if A is not 0 and V is not 0, then the product of A times V is not 0 in this vector space. Right? So the singleton set V is linearly independent. It's by definition. It's hard to do things by definition. We need a characterization of them. So the second lemma is exactly that. It gives us a condition to check if a set is linearly independent. A very important tool. We'll use this tool regularly throughout the course when we are doing what will become very common practice, checking to see if some set is linearly independent. And how we'll check it is using the back half of this theorem. We'll see if it's true that whenever you take some vectors in this set whose linear combination is 0, does that force all of the coefficients to be 0? If that implication holds, then the set is linearly independent. If the implication doesn't hold, it's not. Okay, this video is getting long. I'm looking at the clock. So I wrote one of these proofs out. Let me just kind of narrate us. So work that we've already done above, sorry about that, work that we've already done above is that if you have a linearly dependent set, then there has to be a non-trivial linear combination of the vectors in it equaling 0, right? So that was part of our work above. It was half of that implication. So if you look at the contrapositive of that, if every possible combination that equals 0 is the trivial combination, that's just the negation of that statement, then the thing cannot be linearly dependent. That is, it has to be linearly independent. So half of our theorem is really just the contrapositive of our work above. Okay, I know I'm talking fast, but if you kind of stop and sort out the logic and write out these quantifiers yourself, you'll see that, yeah, I'm rephrasing, because remember, dependent and independent are opposites of each other. So anytime you have a theorem that says like, oh, something implies something is linearly dependent, you can look at the contrapositive and negate things. That's what I'm doing for this part of the proof. Okay, let's look at the back half. What's the back half? Now we're going to suppose that we have a linearly independent set. Because I'm going to suppose I have a linearly independent set this time. And I need to prove that whenever I select a set of vectors with linear combination equaling 0, I must have done it with the trivial combination. All the coefficients must have been 0, right? So the only combination of these vectors in S that's 0 is the trivial combination, is our goal. So let's see. Got a linearly independent set, okay? So suppose I have some vectors, Vj, and some scalars, Aj, and the linear combination of those things is equal to 0. I'm trying to show that at least one of the coefficients is not 0. So for a contradiction, it's a logically complicated proof, but I'm going to suppose for a contradiction that one of these coefficients isn't 0. And then using the same kind of algebra that I did above, if that ith coefficient isn't 0, I can solve this linear combination for the ith basis vector, or sorry, the ith vector vi, the ith element of S, out of that combination. And that shows that some element of S is a linear combination of the other elements in S. But we proved above that that means that S is linearly dependent. And that's a contradiction to, or if you like, I could phrase this as a contrapositive too. That's a contradiction to our assumption that it was independent. Okay? So there, that shows that the characterization of independence that I'm after, the only way you can get a linear combination of independent elements to be 0 is if all the coefficients are 0. It's a nice result, because we know that equations like this in vector spaces lead to systems of equations. Well, this one is a quote-unquote homogeneous system of equation, meaning all the answers are equal to 0. So it makes those operations of substitution and so on easier to do. Let's just look at a really quick example. It's kind of cooked up to be super quick, but if I take, say, this subset of R4, okay, you can pause the video and look at the 4 vectors in it. Right, so there's their coordinates. It's a subset of R4, and I claim it's linearly independent. And I'm going to use that lemma to check it. So I'm being brief here in the notation, but I'm supposing that I took those 4 vectors, I called them here, I didn't write it here, but let's call it V1, V2, V3, and V4. Okay, and suppose some linear combination of those things is equal to 0. Well, then think about the equations that I'd get to that, right? Like, so the when j is 1, I'm looking at the coefficient of this thing. Well, the a1 would get multiplied by this vector, a 0 and a 0 in the second and third coordinate, and then I have a minus a1 there, right? Notice that no other element is going to contribute to the A1 coordinate, or to the first equation, right? Because no matter what you put here, A2, it's times 0, A3 times 0, A4 times 0. So that first equation is just coming from this coordinate, and it's going to be A1. And what does A1 have to equal? Well, it has to equal 0. It's a homogeneous system of equations. All these answers are 0. That's what I mean by homogeneous. Likewise, can you see it? A2 is equal to 0 as the second equation, because you don't get any contribution there. You can pick up one A2 here. A3 gets multiplied by 0, and A4 gets multiplied by 0. Same thing for A3. It only gets picked up right there. So that's the equation A3. The last equation you would pick up. A1 gets a -1. A2 gets a -1, A3 gets a -1, there they are. A4 picks up a 1. So the system in the fourth coordinate corresponds to that. But the first three equations mean these numbers are 0, and that implies that A4 is 0. All right, so the whole argument, if I summarize it, the supposition that this thing was a linear combination that equals 0, we were able to prove that all the coefficients are equal to 0. So lemma 2, we just used it for the first time, we'll use it a lot, says that S is linearly independent. So that's a linearly independent subset. So just circling back through some ideas of this lecture, that means that no element of S can be written as a linear combination of other elements of S. Yeah, if you chose any, say, one of these, you cannot write it as a combination of the other three. It can't be done because it's an independent set. If I could write one of these things as a combination of the other three, that's a dependence. And this system would have had a non-trivial solution because of that. But this system's only solution was the trivial solution, where all the coefficients are equal to 0. And so it's an independent set. Okay? We're getting near the end. I know this video is getting pretty long. There's one more result in here, and I'm not going to really kind of prove it. I'm just kind of narrating the proof. I hope you're reading this book. The proofs in it are pretty explicit. They're digestible. You get a piece of paper out and work along with the author, and it's a good way to learn how to write arguments for this. But here, let's get to it so I don't make this too long. So last theorem, I'm skipping over theorem 1.6. I'd like you to take a look at it, but for this lecture, I'm going to just do 1.7. And so it's about a subset in V that's linearly independent. It's important to know that. So I'm assuming that I have this linearly independent subset in V, and then I'm picking a vector that's not in it. Okay, so you got to kind of have that visualization down, that I've got some collection of vectors. There's no redundancies in them. They're linearly independent. And I pick a vector that's not in it. And then I look at the set. I quote unquote expand the set S by unioning it with V. And if that creates a dependence, then V had to have been in the span of S, and vice versa. That's what the theorem says, right? So if you expand S by something not in it and create a dependence, what you're expanding by must have been in the span of S, right? So you didn't add anything new, quote unquote. Okay, so how does the author prove this? Well, let's just check it out. So first direction, in my handwriting, I would have written that arrow. If that's a linearly dependent set, then you have to have some vectors in it. He's calling them U's. Sorry about that. He's calling them U's. There's 10 of them. Where are they? They're in this set. And there's some linear combination of them as 0. For these scalars, some of which have, at least one of which has to be non-zero. That's just the definition of linear dependent, right? So that yellow highlighted stuff comes from this supposition. It's a linearly dependent set, right? But S itself is linearly independent, right? So these U's cannot all be in S. At least one of them has to equal V, and although the author didn't write it here, I don't blame them, but I'm going to write it explicitly. He's supposing that it's U1, At least one of them has to be V, and he's saying that it's E1. That's fine. I don't mind that. We can rename them. But in particular, then that A1 is not 0. Because if A1 were 0, well, then it wouldn't be in the equation, right? I mean, if A1 were 0, A1 times V is 0. So you'd have this non-trivial linear combination of things in S, but that's a contradiction to S being independent. So good. Are you with me? If you had some linear combination equaling 0, it has to kind of involve this new element V, because otherwise you'd be contradicting S's independence. And the new element V is involved in a non-trivial way. It has a non-zero coefficient, so you can solve for it. It's to be an old trick now, right? 3 times in this lecture we've done this. You have some vector, it has a non-zero coefficient, you solve for it. Because you can divide by any non-zero element in a field. You can divide by non-zero real numbers, complex numbers, whatever field you like. So what is this? This is a linear combination of the other u's, right? And so if V is a linear combination of those other u's, which are all in S, then V has to be in the span of S by the definition of span. Nice. So there's half of it. Directly going for it. Conversely, if you take something in the span, right, then you have to have some vectors in S. He's calling them He's calling them V's. And some scalars, he's calling them B's. And your vector has to be a linear combination of those things. So the V's come from S, the B's are some scalars, V is in that sum. So what does he do? He's just doing what I did, taking V to the other side with the sign -1, right? And why is V not equal to VI for all those values? Yeah, can you stop it and no? V is not equal to all those things because, well, we said V is not in S, right? Those things all came from S. V is not in S, so it doesn't equal any of those things. So the coefficient of V in that linear combination isn't 0. So we've explicitly found a dependence, right? That's a non-trivial linear combination equaling 0. So that set is dependent by what we just proved. Okay, so that was kind of a long one. I hope walking through that proof kind of helped. Sorry about that. Now I'm in really hot water here. Put that back. And I'll just keep it short, and hopefully we'll go over this in class and you can ask some questions about it there.